Okay, so in classical mechanics, matter made from charged particles is unstable. Which sounds bad. And so to see why that's true, let's consider a classical hydrogen atom and see what will happen to it. Okay, so a classical hydrogen atom is going to consist of a point-like proton and a point-like electron. As far as we know, the electron really is point-like, but the proton actually has a little bit of structure to it. It's not quite point-like, but we can ignore that for this purpose. And they're separated by a distance r. And so there's an electrostatic potential between these, which looks like, depending on your units, 1 over 4 pi epsilon naught times the charge on the electron times the charge on the proton, which is minus that, divided by the distance between them. And so the key feature about this is just that it's unbounded from below. Which means that at least naively, if we take the electron and the proton and we shrink their distance to 0, we're going to release an infinite amount of energy by doing so. Okay, so the energy E goes to minus infinity as r goes to 0. And so that sounds bad, or maybe it's an infinite source of energy. Now, neither one of those happens to be true, but it at least sounds like a dangerous instability. And so you could say, well, maybe the thing is that you can't just have this thing fall directly in. Maybe it goes in a circular orbit. But the problem with that is that it can't happen. Even classically, that's not possible because it's unstable due to radiation. Okay, and so the reason we know that is because, so first let me draw a little cartoon of now my electron going in a circular orbit, still at a radius r, which is supposed to be fixed. And so the point is that the electron is accelerating if it's going in a circular orbit. We all know that circular motion means acceleration. And so the acceleration is equal to v squared over r for circular motion, but it's also equal to the force divided by the mass. And so if we take the force from this expression from the potential, this becomes QE squared over m sub e divided by 4 pi epsilon naught r squared. Okay, and then we have from classical electromagnetism, the fact that you then get radiation. So there's the Larmor formula for radiation due to an accelerated charge. And this comes about from Maxwell's equations. There's no way around it once you treat the classical Maxwell's equations in that way. And it says that the power, which is the change in energy with respect to time, is going to be minus mu naught QE squared acceleration squared over 6 pi times the speed of light. Okay, so now we know here's our electron, and it's going to be sending out radiation. And if it's losing energy due to radiation, that's once again an instability. This is, in fact, dipole electromagnetic radiation. Okay, and so now what we're going to do is just take this expression for the acceleration and plug it in right there. And so that's going to give us that this is equal to minus mu naught, the charge to the 6th power, divided by the mass of the electron squared over 6 pi speed of light 4 pi epsilon naught all squared. And then also in the denominator, this is the most important part of the formula, is it goes like 1 over the distance between the proton and the electron to the 4th power. So what does that mean? That means we're going to lose energy, and the closer together they get, the electron and the proton, the faster we're going to lose energy, because we're going 1 over r, and r is getting very small. Or 1 over r to the 4th, and r is getting very small. Okay, so meanwhile, we have a formula for just the energy itself if we're in a circular orbit, which is the kinetic energy plus the potential energy. The potential energy we wrote down earlier, so now I'm just going to rewrite it. Okay, and now we're going to use the fact that we have this expression for v squared over r, which we can use to plug in here, and use that to simplify this expression. So for the energy, and so this, it turns out that what happens is you just get you get the second term with a factor of 1/2 in front. So this is 1/2 of the second term, which is negative. And so it's minus 1 over 4 pi epsilon naught QE squared over R. How are we doing so far? Am I going too fast to take notes? Anybody?
Excuse me, Professor. I was taking notes and momentarily fell behind. Up at the very top, right next to that first formula you wrote.
Yes.
What did you write there? Is that?
Oh, this. So this. That's supposed to say unbounded from below. Let me rewrite it. Oops.
What does that mean?
It just means it's as r gets very small, this thing is going to negative infinity. So it can be arbitrarily negatively large. Unbounded. Sorry about my handwriting. I'm still getting used to this pen. Okay. But it just means if I take r to be very small, then I'm taking 1 over a small number, it's getting very large, but then there's this minus sign, which makes this thing be arbitrarily negative.
Oh, thank you.
Any other questions before we go on?
Yeah, I have a question.
Yeah.
So for right here, like at the bottom, right, where you had like E equals like kinetic energy minus potential, what is it, like, how would you get to that next step?
Oh, so basically I'm just solving for V using,
using
I'm taking this and I'm taking that.
Okay.
I'm solving for V. I'm skipping a few steps, but I'm taking this,
Yeah.
I'm taking that, and I'm plugging them both into there.
Okay.
And then miraculously, it happens that this term has the same form as this term.
Yep.
It's actually not so miraculous if you think about it, because dimensional analysis says they're both parts of the energy, and therefore they're going to have similar forms.
Yeah.
So then that's how you get this.
Okay, thank you.
Good. Other questions?
So basically, that E you're trying to solve for. You're subtracting the potential from the kinetic, correct?
I'm actually adding the potential. So the potential here is a negative number.
Oh, yes. Okay. Now that makes sense. Sorry.
So I'm adding the kinetic to the potential, which happens to be negative, and I'm finding that it's a negative number, but it's given by this expression.
So that's to get the total energy, correct?
That's to get the total energy. So what we've done here is really, we've got the total energy, and we've also got the rate at which the energy is changing, and now we're going to use those to make a differential equation to tell us how fast our hydrogen atom is losing energy and what will the radius do as a function of time. Okay. Other questions? All right, so let's go ahead. So now what we're going to do is we're going to just say the time derivative of this energy, and we're going to set it equal to the power, which we also found here. Okay, so let's go ahead and do that. So d by dt of minus 1 over 4 pi epsilon naught QE squared over 2R. Okay, that's from the E, is equal to what I got up here, minus mu naught QE to the 6th over ME squared. 6 pi C. It's a very complicated constant here, but the most important thing about it is that it's constant. Okay, and clearly the charge on the electron is not changing, neither is epsilon naught. So if I simplify what's in this term, all I'm going to get is something that involves dr by dt with some constants. Okay, and it turns out, so this gives 1 over r squared dr by dt equals, I'm not going to write the whole constant, okay, but it's some combination of stuff times 1 over r to the 4th. Okay, and so that means, if you want the actual constant, that's in the notes. So anyway, that becomes r squared dr is equal to a constant times dt. And so the great thing about this is now we can integrate both sides. Okay, and the integral of r squared dr, we're doing an indefinite integral, so that's r cubed over 3 plus some constant of integration is going to equal t plus some other constant of integration. But whatever it is, I can absorb it into this constant of integration anyway by moving it to the other side of the equation. So let me just, in fact, erase that. Okay. So another way of writing this is, if you're very careful to keep track of where all the constants are going, is this is going to amount to r cubed minus r0 cubed. R0 cubed is just my name for some constant, is going to equal minus a constant I'm going to call k times t minus t0. Oops, I've made a mistake here. There should have been another constant multiplying this. That constant is the constant that comes from the mu naught QE to the 6th over ME squared and the C and all that stuff, if you do all the algebra for that. So that's just being absorbed into this constant, which again is given in the notes. So the minus R0 cubed is some combination of constants of integration. So is the T0. And so the way I've set it up here is just so that by choosing the constants of integration, I've chosen things so that R is going to equal R0 at time t equals T0. Okay. So another way of writing this is R cubed is equal to the initial value of the radius times 1 minus k over r cubed times t. Okay, or by advanced methods by taking the cube root. Oops, that was wrong. So r is going to equal r naught times 1 minus kt over r naught cubed to the 1/3 power. Okay, and so as promised, what does this say? This says that the radial coordinate of the electron as it goes around the proton is going to go to 0, but it doesn't just sort of fall in slowly or asymptotically approach 0. It actually gets to 0 in a finite amount of time, because if I graph as a function of time what r is, and I'm starting from fixed radius r0, when is it going to actually reach r equals 0? It's going to reach it, if I go back to this equation, that's going to tell me that it's going to reach r equals 0 at the time 1 over k. Oops. Okay, or perhaps it's actually easier to see it from this equation right here. Oops. From this equation. So if I just plug in r equals 0, then it can only be satisfied when t is 1 over k. I seem to have some sort of issue with units here, but okay. So in any case, your homework, your first homework problem, is to straighten out all the arithmetic, figure out what the constant k is, and figure out what is, if we graph this as a function of time, oops, what is the lifetime of the hydrogen atom in this classical world? Okay, so the atom reaches r equals 0, which means the energy is minus infinity in a finite time. So if the world really worked this way, then this would be a source of free energy. Unfortunately, that's not true. But what does quantum mechanics do to avoid this? Well, first of all, there's a similar instability that's more complicated to work out for larger atoms, or even not atoms, but crystals. So any form of matter made out of charged particles is going to have the same problem. Basically, your negative charges and your positive charges are going to be attracted. There's no reason why they can't just glom onto each other and release an infinite amount of energy, and the whole universe would be unstable. Okay, so what does quantum mechanics do? It changes the rules. Okay, and so first of all, not all configurations are allowed in quantum mechanics. Okay, and so in fact, there is no state where r equals 0. Classically, there's no reason why I can't have my electron and my proton come arbitrarily close together. But quantum mechanically, we're going to find out that's just not allowed. It just doesn't happen. Okay? The energies of bound states are quantized. What does that mean? Quantized just means discrete. That means there's a fixed set of them that you can have, and going back to the previous point, you can't have certain other ones. Now, it turns out the energies of unbound states means things where the electron can wander off as far away as it wants. Those are going to remain continuous, just like in classical mechanics. And so one of the things we'll want to find out in this course is how to explain why that's true. Okay, let me pause to see if there are any Other questions or things we can clear up on this? Okay. All right, a second issue. Oh, sorry, go ahead. Was there a question?
Yeah, sorry. So when you said the homework problem 1, can you also reiterate real quick what the actual steps, or not the steps, but the parts of that one was? Because you said find like the constant K, find the lifetime, right?
Oh, right. Let me actually bring up the homework and look at what I actually asked you because I don't quite
Oh,
remember.
that was okay. Yeah, that's right.
So-
You gave the homework. Okay, gotcha.
Yeah, so actually on the homework, it's that first problem, all you're really doing is plugging in the numbers.
Okay, that's fine.
Yeah, so it shouldn't.
Sorry about that. I forgot that that was already given.
Yeah, yeah. So you're just going to be plugging in the numbers. By the way, the homework set 1 is available on the web page, and I guess I didn't mention how you should turn in your homework. So you can turn in your homework. I prefer it each homework set as a single PDF file, if you can possibly manage it. You can on campus, the copy machines will actually scan in paper and produce PDF files, which it will mail to you, and then you can mail it to me. If you don't want to bother with that, and I don't necessarily blame you if you don't want to be spending a lot of time at the on-campus copiers or scanners or whatever they are, you can take picture with your cell phone. Just try to make it as legible as possible so that grading can go smoothly. It's also a good idea if you don't write too small and if you leave a little bit of space on your homework sets so that I can put in grading and comments on that.
Fun fact, just in case it might help anyone, for homeworks, I use an app called Tap Scanner that you can just get on your phone, and it'll take your pictures and make a PDF, and it'll make it look like slightly nicer than just with your phone camera. So, fun fact, if anyone wants to check that out.
Great. So what was the name of that again?
Tap Scanner.
Tap Scanner.
Office Lens is also a good thing as well to do that. It does the same thing. Office
Lens. I'm guessing at the spelling.
Yeah, that's right.
Okay.
I also had another question.
Okay, good.
So when you solved for the time as R went to 0, you just had 1 over K. I'm just confused what happened to R not cubed.
Yeah, as I was saying, I was confused about that myself. I think I think I changed my mind on what the K was between what I'm doing in here and
okay, so you just combined it into it.
Yeah, so what you should do is, and this is a general thing, is you should always believe what's in the notes compared to what I say in lecture, because in lecture I might take a factor of 2, or in this case I think I've put in an extra factor of R0 cubed. Basically what I've done is I've redefined my constant. So my constant K here is not the same K as what's in the notes.
Oh, so in the notes they combine your K and R naught cubed to make their own just constant.
Right.
Okay.
So believe what's in the notes always.
Okay.
Over what I say in lectures, unless the notes have some inconsistency, and then you should tell me about it to get your free point.
Okay.
Okay. Good. Anything else? All right. So let's continue on with our little survey of things where classical mechanics doesn't work out right. And so the next topic is the fact that light has particle-like features. And by particle-like, one of the things I mean is that it has discrete features. Now in the notes, there's a section about black body radiation, which you should all read, but I'm not going to actually talk about that in lecture. We're going to skip that, but that's section 1.2, I think, of the notes. Instead, I'm going to skip to the next section where we discuss the fact that in classical physics, there's no reason why you can't vary everything, every quantity associated with light continuously. And that means things like the amplitudes. The amplitude is given by the magnitude of the electric field in the wave, and the energies of electromagnetic waves, and the frequencies of electromagnetic waves. Maxwell's equations are linear, which means you can just put together any frequency and amplitude and energy that you want, basically. But in quantum mechanics, what we find is that we're stuck with what are called photons, where light comes in discrete chunks. And in various versions of this, in the black body radiation example, that was found by Planck. And in the photoelectric effect, which I'm actually going to talk about just briefly, that was done by Einstein. But basically, the chunks always have energy equal to a constant multiple of the angular frequency. And that constant multiple is called h bar. And h bar is equal to, this is an important number, 1.05457 something, 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 times 10 to the minus 34, so it's a very small number, in everyday units, which in this case are joules times seconds. And then sometimes it's more convenient to write it like this instead in different units. Still a very small number, but this is in electron volts times seconds. Okay, so in any case, h bar is an energy times a time. And it's some constant of nature which goes in there. We also often will talk about h, which is the original Planck's constant, which is just 2 pi times h bar. This is a constant that Planck had to invent in order to understand or explain the black body radiation. Now, going along with that, and this is really with Einstein's special relativity put in, we also have that the momentum of a photon is h bar times k, where k is 2 pi over the wavelength. So once you decide on the wavelength, then you know the frequency, and then you know the momentum and the energy. Okay, so what is the photoelectric effect? This was an experimental fact which was explained by Einstein. This is why he actually got the Nobel Prize. It wasn't for relativity. And so the idea is, if you shine on a metal surface, if you shine a piece of light, which I'm drawing by a wavy line, you can eject an electron, which you can then gather and form some current. And basically what Einstein proposed, or what was actually experimentally observed, is that this requires a specific minimum energy. And since the energy is related to the angular frequency up here, that means that if omega, the angular frequency, is too small, then no electrons are produced by ejecting from the metal, no matter how high the intensity of the light is. So let's say your light was red and that this was zinc. You could have the most powerful red laser in the world and shine it on this zinc metal, and the first approximation, you would never get any electrons coming out. Okay? And that means the number of photons. That's the intensity of the light. So instead, what happens is if you graph the minimum kinetic energy, I'm going to write Ke for kinetic energy, as a function of the frequency for this. And this is going to be, for example, for zinc. Okay, then what happens is it looks like this. It's 0 until you get to some value which turns out to be in the ultraviolet, and then it rises linearly. Okay, and the slope of this line is actually h bar. Okay, this number right here, this number right here is about 6.5 times 10 to the 15 radians per second. And so this is where the visible is. As I said, you can send in red light all you want. You won't get any photoelectrons coming out. And this is in the ultraviolet up here where you can start to get electrons coming in. Okay, and so the interpretation is that the energy of the photons, h bar omega, is too low for the visible spectrum. And so this was evidence that light really did come only in these discrete chunks, because when you're down in the visible, if you didn't have one of these photons with enough energy, this event that's occurring up here, would not be able to occur. All right, so we are out of time for today. And so I'm going to stop the recording here. But if you would like, if you have any